This video is part of a course on food physics, of which this belongs to the theory section. The subsection that this one is belongs to the governing equations for single phase mass transfer. The immediately preceding video is the governing equation for heat transfer, and the immediate follow-up video is the derivation of the equations, the governing equations for fluid flow. While the equations are complete here, they're not meant to be a replacement of a course on transport processes. So this is done more in the sense of a follow-up of a course on transport processes, but it is complete in terms of its derivations. The mass conservation equation that we are about to derive is a mathematical statement of conservation of mass. It is implemented, it is formulated by doing a mass balance, which is very much like the energy balance that we did in the past, but this is on a species. And what do we mean by a species? So here we have water and we have a dye. So the dye is diffusing in the water, or it's also moving with the water. And it is the dye that is the species on which we are going to do a mass balance and develop the mass conservation equation. So to do that, we have to really define a system boundary. And so here is the system boundary, the red line here. And once we have defined the boundary, then we can say that the rate at which mass is into the boundary minus the rate at which mass is leaving the boundary plus any generation of mass should be equal to the rate of change in the mass stored. So this is the storage. So in other words, all we are saying is everything has to go somewhere. And that is the statement of the mass conservation. And so we're going to now see how we write these terms, the in, the out, and generation. So the first one we want to look at is, what do we mean by mass generation? Here are two examples of mass generation. A mass doesn't have to be a significant, of weight or anything. It is just the amount of a particular species. For example, the amount of bacteria by weight inside this can, of course, is going to be negligible even in the worst scenario, but we can use the mass conservation equation on bacteria inside this can, and we can talk about heating this can and destroying this bacteria. So if the bacteria gets destroyed, then with bacteria as a species, it has a negative generation given by an equation like this. So you see there's the negative sign, means the bacteria is getting eliminated. So another example would be, let's say in this frying process, we want to look at how acrylamide, a carcinogen, gets formed. So longer we heat, more carcinogen is forming. So then we have an equation that says the rate at which this acrylamide is formed is given by this. It's a complex equation, but nevertheless it tells me what rate acrylamide is generated. So if I am doing a balance, a mass conservation on acrylamide, then all of this would be my source term, and it's a positive one. Now I want to see how we can write these in and out terms in terms of mass fluxes. To write the fluxes, let's look at this simple system of two different gases together, the red and the blue. And the red, blue, they're both moving randomly, so red is diffusing into the blue, as you can see. And so I want to write the flux of red into blue. For that, I have drawn this imaginary line at which I want to write the flux. So the diffusive flux is simply diffusivity times the concentration gradient at this point. Okay, so that's my diffusive flux from Fick's law. If we look at the units, so that it gives us a more tangible feel for what these quantities are. So diffusivity is a measure of movement, and it's meter square per second is the unit for this. And del Ca del X, concentration, this guy is kilograms per meter cube, mass per unit volume, and divided by the gradient meter. So that gives me kilograms per meter square per second. So it's a flux and a diffusive flux. So at this point, the way you see the animation, all you have is diffusive flux. However, the gas can move as a bulk, and that would look something like this. So that is on top of the diffusion. Diffusion didn't go away. And so that flux is the convective flux. And again, let's look at the units. U is the velocity. U is the bulk velocity with which this gas is moving. And so that unit is meter per second, and the concentration units are kilograms per meter cube. So that again gives this kg per meter square per second. So this is my total flux. This is my total flux. So in general, I should be using this total flux, which has a diffusional component and one due to bulk flow. We're going to use this term now to derive the mass conservation equation. With mass fluxes defined and mass generation discussed, we now want to put everything together to derive this mass conservation equation. So basically we're going to put all those flux terms and the generation terms into this mass balance, the in minus out plus generation equal to change in storage. So for this we need to define a control volume. So let's look at a control volume that is fixed in space. So here we have a fluid, and I don't know if you can see this, but there are little dots. That is the species that is transporting in the fluid, meaning it's diffusing, plus it may be moving with the fluid, and it is this species that we are writing the conservation equation for. And this control volume is fixed in space. Now back to this species, the reason this equation is called dilute species conservation equation is the species that is diffusing. So let's say it's A that is diffusing in B. The amount of A is small enough that it, by the diffusion process, it is not having any impact on the B. It is not changing the B by the diffusion process. This is not always true, but for now this is the simplest case, and that's what we're trying to derive the equation for. It is the most applicable one. It's the one that we see all the time. Okay, so this control volume, which is enlarged here, is of size, it's a cube of size delta x. Let me do that. Delta x and delta y and delta z. So it's a cube of those dimensions. And let's try, and so the species A would be coming in to this control volume by diffusion and by flow, and then going out by those two mechanisms also. So we're only going to look at these phases where things are entering or leaving. Okay, so what are the fluxes? The flux law says diffusive flux, this is the Fick's law, is minus the diffusivity times del Ca del x. So let's define the quantities. DAB is the diffusivity of this species A in B, and Ca is the concentration of species A at any place. So we can think of, for example, kilograms per meter cube, let's say. Okay, so concentration units, and x is the position variable. So del Ca del x gives the concentration gradient. So that's the diffusive flux. And then the convective flux, we have already discussed this. It's equal to u, the velocity, in this case of really the phase B that is carrying the species B that is carrying species A. So the species A's velocity is also this A, and we have these two together. They make up the total flux. This makes the total flux. So we're now going to say, using that total flux, how much comes in through this phase, which has the same dimension as this one. So what's coming through this phase is minus dAB del Ca del x plus UCA. So that is the total flux, and the unit of that is like kilograms per meter square per second. So per meter square, so we have to multiply by the area. So area is delta z times delta y. That gives me, so this times meter square, so meters cancel, and so you get kilograms per second. So let's do a balance over time delta t. So over time delta t, I multiply by seconds, so that gives me kilograms. So this is the kilograms that came in through this area over time delta t. And it's the same way we write the expression. So this is in, and so then this is out, because now I'm writing the same expression but at x plus delta x. That's very important. And then multiplied by the same area and time. Okay, so inside, as the material is moving inside, it can also get used up, or more of the material can get generated in a general way. And so RA is my rate of generation, and it's kilograms per meter cube per second. So inside the control volume, that's where we're writing the balance on. So inside, how much is generated over time delta t. If this is the rate is kg per meter cube per second, then we have to multiply by the volume of that element plus the time duration that we are talking about. Okay, so that is my generation term. This is my generation term, and because of stuff coming in, out, this arrow, it's going out from this surface, and plus generation, there's going to be more or less of that species inside this control volume. So in other words, the concentration, the amount inside will change, which means the concentration would change. So how much is this change? This is the change in storage. So the amount that will change, if we think of concentration as a unit of kg per meter cube, okay, so then del Ca stands for how much is the concentration change, how much is the change in kilograms per meter cube, multiplied by the meter cube, so that gives me kilograms of change. So then every term is in kilograms. The first one, this one is what came in. Likewise, the next one is went out, plus the third term here is what is generated, and because of that we have a change in storage. And so that is simply a mathematical statement of this term. And now we try to simplify. So how we simplify is we divide throughout by delta x, delta y, delta z, delta t. So if I do that, you can see that, for example, the storage term becomes this one, del Ca, del T. Then the convection term, UCA, if I collect these two terms and rewrite this way, UCA delta x plus UCA at x plus delta x minus UCA at x, and because of the division I get a delta x at the bottom because this delta y, delta z, delta t cancels out. And the diffusion term, likewise, I can write in terms of x plus delta x minus the same quantity at x, and again I get a delta x at the bottom. And then RA is my generation term because we are dividing by delta x, delta y, delta z, delta t. All of these quantities will go. Okay, so we are almost there. Now we say we make delta x and delta t go to 0. So from a balance with finite quantity, we want to get to infinitesimally small quantities or a differential equation. So let's write the differential equation now. So del Ca del T, like this one becomes del Ca del T. So the next one, you have something at x plus delta x minus something at x divided by delta x, with delta x going to 0. That gives you the derivative. So it's this one, and likewise this one, except I did the special thing that I took dAB out of the outside of derivative. That you can only do that if dAB is a constant. Okay, so that's how we get the second derivative, and plus RA. Okay, and in a very general way we can write this equation as del Ca del T plus del dot UCA. So this is the convection or due to flow, and then this one I put the d back inside the derivative, and this is due to diffusion. Okay, and so this, when we try to solve this equation using a commercial software, then they implement this very general version of the equation. So it can take care of lots of different situations, different geometries, properties, and so on. So this is my transport equation, and we'll spend a little more time looking into it in just a second. So applying this equation is easier if we relate this term to the corresponding physics that it represents. So we don't get worried about the equation looking big with many derivatives and so on. As long as we keep track of what they represent, it's not bad because we often solve it using a commercial software. So we're not doing the detailed math on our own quite often for practical problems. So it's very important we need to keep track of what these terms represent and so on. So first term here, this one, it's change in concentration with time. So concentration changes with time if it stores more or less. So this one has to do with the rate of change of stored mass. Rate of change of stored mass. That's what this term represents. So the storage part, if we think of a finite volume, then the storage part is what this one represents. Of course, this equation is valid at a point, but I am just saying this in sort of a kind of a quick and dirty way, that the terms relate to the in-out generation and storage that we started from. And so the second term is it has the velocity, which means it has to do with flow. It's how much stuff is flowing in and flowing out. What is the net rate of mass change due to just flow? Likewise, the third term, and I should put a diffusivity of A in B, so this has to do with how much is the net amount diffusing in. So it's not just in, it's of course diffusing in and diffusing out, but what is the net rate of the mass change inside due to diffusion? And then the fourth one has to do with the rate of generation, or it could be degradation, which is a negative generation. So change in the mass in this control volume due to generation or degradation. So of course, again, the equation is valid from point to point. I just use this diagram from the past to illustrate the physical meaning of the quantities. So the governing equation that we derived is very general, and so general that it has many terms and it can look scary. But the point is, and I would like to draw this analogy at this point with the Swiss Army knife, that even though it has many different tools in it, we don't need all the tools all the time. So likewise, this general equation, it has all the terms we need because it's coming from fundamental principles, so it has every piece in there. But that doesn't mean in a real world problem, we need all of those terms. And then the other point I want to make is it can be made even more general. So let's look at the details of the general aspect of this equation. So we realize that we didn't assume any particular type of food or non-food or anything. So it's very general. As long as it's a dilute species and there is diffusion, there is flow, we can use that equation. So it's very, very general. So we can use that for any component in any material. We can use that for any size or shape. And most importantly, starting from this general equation is very safe, because as you drop terms, we are very aware of what physics that we are not including. This is much better than going ad hoc and trying to develop a simple equation and then trying to build in complexity. Now, this equation can be made more general. We just derived a baby version, a 1D equation with constant properties, and we can make it much more general version. And for example, we can develop a general version that's in 3D, or for a shrinking system where the dimension keeps changing. All of these are still going to be called the species mass transfer equation. So we have derived effectively the mass transport equation that we need. Just for completeness, here is an example of the mass transport equation in the different coordinate system, in Cartesian, cylindrical, spherical, and the most general form. So here, just for convenience, just to make it less messy, we have dropped the convection terms. But convection has to do with flow, and as long as flow, we need that term. We just happen to have dropped it here to keep it clean. When we solve analytically, then we have to worry about this choosing Cartesian, cylindrical, or spherical. But when we solve numerically, the software typically implements a very general version, and we don't worry about using exactly which equation. Limitations of the equation, at least in the form that we derived, is something we should talk about. And the first one I want to share is when the material is shrinking, the equation needs to be written in more general form. Then another one I want you to see, the diffusion equation is a very general one. It can be, it has terms due to diffusion, flow, and also reaction. So let's say in frying, I want to calculate how much acrylamide forms. Acrylamide is a carcinogen, and we would like to know at high temperature, when you're heating starch, it forms, and how much is it forming with time and with location. Well, we can use the diffusion equation with the acrylamide generation as a source term. Now that sounds great, except the acrylamide kinetics and its temperature dependency, that needs to be known. And that kind of information is not easily available for various food systems. In other words, we can have a nice transport equation, but it needs parameters that are sometimes harder to get and not easily available. Then in another example where things can get difficult is when there are other modes of transport than just diffusion. So for example, in bread baking, of course, there's pressures generated inside the dough. That's what puffs the bread. So there's pressure driven flow. And while pressure driven flow can be included as part of the fluid flow term, but to be able to do this right, we have to think of the food as a porous media, and we also have to bring in additional phases. So for example, it will be water and vapor. So that kind of situation then would need some sort of averaging, because as you can see, there's pores and so on. So we have to treat the food as multi-phase porous media, going beyond this single phase equation. And this topic is in a separate module that we have. We go in fairly detailed on how to develop the equations for porous media transport based on the very equation that was developed in this module.